Hey, this is Mr. 8 and this is Physics Honors, and we're going to be doing ray diagrams for mirrors. So before we did ray diagrams for lenses, but now we're going to do ray diagrams for mirrors. So which means we're going to figure out what happens when you look in a mirror. How is this going to be taking a look with light? And so the amazing thing is our thin lens equation for a lens would be 1 over the focal point equals 1 over the distance of the image plus 1 over the distance of the object. And the magnification was hi-ho, negative d-do. And guess what? It's the same equations for mirrors, which means if you could do the lens equations and the magnification equations for lenses, guess what? You can do them for mirrors. We have one last equation for mirrors is a mirror, one that's curved, is going to have a focal point which is half of the radius or half of where the center would be. And I'll explain that in our first mirror. So we have two different types of mirrors. We have concave mirrors. Those are mirrors that are caving in. And we have convex mirrors, mirrors that are convexing out, I guess. So sometimes we call them converging mirrors and diverging mirrors. Looks pretty similar to what? Your lenses, doesn't it? Very, very, very similar to your lenses. Keep that in mind. So here we have an object. I'm going to call that object O. And so this object O is, you can see, is right here behind my focal point. And you can see my center. If I continue this mirror, this same mirror in the same curvature, you can see how that center is right in the center of that mirror. That is a really poor diagram, but you get the point. Which means the focal point is exactly half of where the center would be. So let's take a look at our ray diagram here. So what's happening to my light? My light, I'm going to use, remember, for my lenses, I had two rules. One was it went parallel, and then it went through the focal point. And they went through the lens because lenses are transparent. But mirrors, it's going to go parallel and then through the focal point after reflecting. So you can see my first rule is exactly the same, whether it is a mirror or a lens. And so you can see how here it went to the mirror, and guess what happens? Bam! It reflects. It doesn't refract, it reflects because it's a mirror through the focal point. That was my number one rule. My number two rule was what? Straight through the center, right? So here you can see how this guy, it's going to go straight at the center right here. And you can see if it was a lens, it would go straight through the center. But here it reflects at the exact same angle. Okay? Remember the angle to the normal. This angle right, and I'll draw this angle. This little angle right here and this little angle right there are going to be the same because it's the law of reflection. Where do these light rays meet up? These light rays meet up right there in my image. Okay, and you can see how my image, it is a real image, isn't it? It's a real image. And so why is it a real image? It is the light rays are meeting together. It is an inverted image. It is an inverted image. Why is it inverted? It's upside down of the object. It's on the other side of the mirror. So if you are behind the focal point on a mirror that looks like this, what we call a concave mirror, you're going to always see a real image and you're always going to see an inverted image. Now, what are we going to find a image that's larger or smaller? Well, that depends where this object is. And so I'm going to go to kind of a simulation here. You can see if this object is behind this center point, can you see my image is always going to be upside down, inverted, and it will always be smaller. Okay, smaller. Once we hit exactly at the center point, it's going to be the same size, and then between the center point and the focal point, it's going to be a larger but still inverted image right there. Okay, And so that the size will depend on where this image is, sorry, where this object is. This object is between the focal point and the center point, so this image is a little bit larger. If it was behind the center point, it would be smaller. And so you can see how if I have this type of mirror and I am far away, everything is going to be upside down. Okay? Now, what happens if we're at the focal point? Let's take a look at when we're at the focal point. At the focal point, you can see what's my first rule is we're going to draw a ray diagram, a ray that goes straight through parallel to the mirror, and then it's going to reflect through the focal point. Okay? And then the next line is going to go straight through at the center, and then it's going to reflect at the exact same angle. And that's about the exact same angle. Now take a look. Will these light rays ever meet up this way? No. Will these light rays ever meet up on the other side virtually? No. Which means the light rays are going to be parallel, which means what do I know about my image? There is no image. So right away you can see how in this ray diagram of a concave mirror, it looks very similar to my lenses. When I'm at the focal point, very similar to my lenses. No image. Now what happens if I'm in front of my focal point? Now think of my lenses. What happened with my lenses when I was in front of the focal point of this kind of converging lens? Remember, we had a virtual image. It was much larger. It was magnified. That's why, because I had a magnifying glass. Okay? So let's see if this depends on the same way. And you can see how here I am going to be parallel. It's going to reflect through the focal point. Okay? And then I'm going to go straight to the center of that, and it's going to reflect off. And you can see how at the same angle, I'm trying to get the exact same angle. That's probably pretty good. Not bad. Okay? Remember, I'm trying to get the same angle right here and right here, right there and right there, the same angle, because of the law of reflection. Are these light rays ever going to meet up on this side? No, which means now I know I'm going to have a virtual image, which means I have to do dotted lines. Okay, so let's do some dotted lines. I want to do that dotted line in blue. Let's see if I can change that to blue. I have a Zoom meeting in just a little bit. And I'm going to try to change that to blue color. What do you know I did? I'm pretty awesome. Yes, I am. And then you can see this guy is going to be blue. And what do you know? There's my image. Look at that image. They met up on this side, which means it is a virtual image because the light rays did not meet up. It was a virtual image. What can you say about the size of this image? The size of the image compared to the size of the object this is much larger image. It is magnified. And what do you see? It is going to be an upright image. It will be the correct orientation of upright, but it's going to be virtual and larger. If you're a woman, you know this type of mirror because you see it in bathrooms. One time I was in a hotel room and they had this big concave mirror, and guess what? When I walked really far away, everything was upside down. And then when I walked really close, everything was magnified, so you could put on your makeup and stuff like that. I didn't put it on in makeup, but you can see in this picture, I love this picture, her hand is really, really close. It's really, really, really magnified. But look at the bench. The bench is really far away, past the focal point, which means it's upside down. So we actually use these mirrors, especially women use these mirrors in order to put on makeup because they can see every little crevice of every little blemish, and they can figure out whether things are working the way they should be or not. Men, yeah, we're fine with just a regular mirror because we don't really care what we look like most of the time. We just kind of, yeah, good enough. We're hairy. We're men. Okay. So this was a concave mirror. Now what about a convex mirror or diverging mirror? You can see how right here, it's kind of weird. Here's my object. My object is over here, which means you could be your object. You're standing on this side of the mirror. okay? And this mirror is bent this way. Well, what do you know is the center is in the center of where this mirror would be. Okay, if you continue this mirror on, you can see there's the center. The focal point is inside that mirror. Okay, and so let's take a look at our ray diagram. Our ray diagram of my first rule is parallel line to the mirror. Okay, now remember, this is the tricky one of how to draw. The rays are going to reflect, aren't they? But they're not going to reflect in, they're going to reflect off. It's a diverging mirror. And they're going to reflect off at the same angle as your focal point. Okay, the same angle as your focal point. Remember, this was the tough one. And so you can see I just did a little bit of an angle, and that is what's happening to that mirror that way. The next line is going to be, it's going to be straight through the center. Do you see where that center is? Right there. Okay. But what happens is when it hits that mirror at this same angle right there, at the center, it's going to bam, bounce straight back, because that's actually hitting exactly 90 degrees to the mirror. Exactly 90 degrees to the mirror. Now you can see, are these light rays going to meet together? No, they're not. Which means we have to draw virtual rays. Okay, one virtual ray straight through the focal point, one virtual ray straight through the center right there. Okay, do these virtual rays meet up? They sure do. They meet up right here, and you can see how that image is a virtual image. This is the toughest one to draw, I think. Just like the diverging lens is the toughest one to draw, it is a much smaller image, but it will be an upright image. It will always stay upright. If you have a convex mirror, you can see how wherever we put this mirror, it's always going to be upright. Sorry, wherever we put this object, the image is always going to be upright, but it's going to be smaller. Now, where do we use this in the real world? We use this for many, many, many different mirrors. We use this mirrors to give us a bigger range of sights. So we put these mirrors at corners so that you can know if there's someone coming the other direction. We also put this little convex mirror on your rear view mirror or your side view mirror, and you can see, what does it say on your side view mirror? Objects in the mirror are closer than they appear. Because the image is going to be smaller. What does our mind think if we see a smaller image? We think far away, but that object may be actually closer than they appear. But why do we use this convex mirror? Is because we can actually see a greater range. There's less blind spots than if we used a straight mirror. So we use this to our advantage, but the images are always going to be smaller and always going to be upright. That's why we don't want to use a concave mirror, because things far away would be flipping upside down. Things close would be magnified. We would think they were right up on us. And so we use mirrors for our advantages. Hopefully that helped. That was ray diagrams for mirrors. If you know how to do ray diagrams for lenses, you know how to do ray diagrams for mirrors. They're the exact same thing. Same thing with your equations. Have a great day, physics. Do your self-assessment on ray diagrams for mirrors. See you guys.